Welcome, ladies and gentlemen. Here's episode 7 of our coding of an AI art generator from scratch. This is episode 2 of printing our neural network. This is a powerful debugging strategy where to a CSV file we can open in Excel. We'll see all the values of our neural network. So here's where we left off last time. I deleted all the files we made, but there happens to be a program right here that'll regenerate that for us. So we'll CMake, build, and run it. Okay, built, ran. And let me share my screen. Here we go. So here's our folder and our CSV. We open it. And we've got our input layer, our first layer of filters for our convolutions, and then the raw output, which are a direct result of our convolutions. So we see here to help with debugging, make sure we have our indexing correct. Our input layer is has its data right now as just 1/100th of the thread ID. So 0, 0.01, and so on. We process with our filters, and then we get our raw data out. And also powerful about using Excel, yesterday we tested that these values actually make sense. So we can apply a convolution to our input values, and the results match our output values. So we're off to a pretty good start. Also, what we want to do next is print our activated data. So after we get our raw output data, we'll apply an activation formula to our data, just cell by cell. There's no intermingling like there is with convolutions. But before we print it, and this is key here, we want to generate the data, which we haven't done yet. So that'll be our first step, is generating our activated data. And before we do that though, we'll just, we will not activate the data, we will just pass it through and make sure all the data's match. All of these values of the data match, just so we know we're printing correctly and we are indexing our neural network correctly. So within our neural network implementation file, mnis_neural_network.cu, we will make our activation function. All the other functions we've written so far with CUDA, they spawn from the CPU and then they instantiate and run onto the GPU. This is the first time we'll run a function that gets called from within a kernel function. So from within a function that gets spawned from the GPU. So the keyword we use for that is __device__. We're going to hit to the compiler to inline it, and we will be passing out our neural net float value. Name of the function activate, and we'll pass in a function we'll name a variable we'll name in. So right now we're not doing anything. This is just a little bit of sanity checking going on at first here. So we'll make this a special case, activation nothing. We want this defined, so we go to our CMake list and we'll put it, we have a target, we'll have a compile definition here for our debug mode. We will make another conditional statement where we define activation nothing. Now for some reason this won't actually inform our RVS code. So as you see here, it's not highlighting this as if this is defined. And that might be typically the VS Code has, with its CMake extension, will parse your CMake file and then update your code and highlight and darken things correspondingly. But it might be, I'm guessing it's because it's a CUDA implementation file. So I'm not quite sure there. So in order to pass this into CMake in the first place, we'll change our command line. So when we call our CMake executable, that is the time that we will pass in this variable, this setting. Now it's just dash uppercase D, then we put in the variable name, and we have to assign it a value. When you pass in something to CMake through the command line, you have to assign a value, unlike with the C preprocessor where you don't. So we assign it to 1, and right now this will only exist in CMake as this function's called. It's not until the CMake variable itself is detected in this if statement where we will create a preprocessor define of activation nothing. So these are essentially separate variables. This is a CMake variable, and this is our preprocessor one. We'll just name them the same thing to confuse everybody. All right, and now let's make sure this works. So here's where our convolution is for our first layer. And now we'll go in and we're just taking the raw output and we're activating it. We already have here from our previous work exactly what we need. Only threads that are less than the first layer output size will get activated. So we're activating our raw output. Let's put that in there. And this data is named first layer activation output. So it's saying it's not seeing it, but it is. It's within the namespace. So good. So that's all it takes to do a completely fake and useless activation. Now let's, do we want to print it first? No, let's just make sure it compiles. Am I forgetting anything? I don't want to have my first compilation error live on stream. All right, great. I've still never had a compilation error in my code in my entire life. And this was my first warning. This libcmt. All right, looks like it ran, generated our file. Now let's print this out. So that is our file writer neuralnet.cu file. Here is where we print our labels. So print, I'll add in a comment, print data labels. I won't capitalize the first letters because this is not a title. Print data. Just gonna check my stream here. All right, here we go. Now, there's something I was thinking about I want to change. The way we have it printed, the way we have this running and writing to file is first we iterate through all our rows. Well, that's the outside loop. So we'll go row by row and we print all of these lines. In our inner loop, we go column by column. So we check here with our loop, if the column we're on is less than the input data width, then we'll print the corresponding input data. These are our data gaps. We've defined them as 3 so that we have some breathing room here. And it's a defined value, so we can change it easily. Oh, we should test that tonight. And then we use a series of ifs. Well, we start with an if, and then we use else ifs. So we're saying that, like, okay, if we're on a column that's less than the width of our input data, then we're printing this. If we're on a column that's less than the data gap plus the input dimension, then we're just going to print blanks, which in the CSV is a comma, and so on and so forth. But what I thought of is that it's looking kind of ugly. Each of our else if statements, these are getting longer and longer and longer. The columns that we want to print below. So let's kind of make these compact. This is an if else if statement, so we have to go before our if statement. Let's not use that. We'll say int layer 1 data gap 1 equals, so we just want the column number that we'll print below. Oh, I copied that. I copied one I should have pasted. I seed one I should have bead. So layer 1 filter column. So here we'll have our layer 1 data gap 2. Now we have our raw output data, so we'll add this in. Then we'll have our data gap 3. And finally it'll be our activated column. And our activated is the same as our raw column width, which is our first layer output dim. All right, so then we'll just start pasting these in where we need them. Data gap 2. Raw. So after our raw data, we'll have another data gap. This is data gap 3. See, isn't it nice when you're organized? And here we'll have our activated output data. So this is layer 1 activated. Now this value here, I think it's just going to be we're going to subtract the column that comes up to it, which would be the end of where the data gap is. So here for this column, yeah, looks like we can just use the variable from the else if statement beforehand. So this one here, input dim plus data plus print data gap. And data gaps don't have any variables like that. Spelled this wrong, I knew I was going too fast. And yes, that all the remainings are just more commas. And then we have a new line when we get to the last column, because our outer loop is our column. Let's think about this. So we have our input data, filter dimension, just add a gap. For raw, we had our output dimension, data gap 3, print, just add another gap in. Column, we had our first layer output dim. All right, I think this will work. Let's see. This will definitely compile, so I'll never have a compilation error for my whole life still. Yep. I'll probably make it to retiring without having a compilation error. Oh, of course, though. Oh, wrong project. We want to print our activated data. Oh, pause the build. Still no errors. Ever in my life. I'll ignore these. Red means stop not making any errors ever. Activation output. Layer 1 activated column. What could our issue be here? Layer 1 activated column. Data gap 2, data gap 3. Let's check the value here. Activated column is, yep, this state. Oh, and then this should be that. Okay. Gotta get these variables in line. Voila! And it looks like they're indexing properly. Hell yeah, guys. Hell yeah. Ladies and gentlemen. Now let's activate it. Let's get some real activation in here. So our implementation file. We'll say elif something different. So here's our real activation function that we'll be using. And this is one that I thought of. So it's my invention. Cite me in your papers. What's typically used right now is a leaky ReLU, and we've been over these. We've been over this as well. This is a ReLU that allows for negative numbers, and from -1 to 1 the neuron will stay the same value. If it's above 1, we'll apply a slope to it, which we have in a defined value right now set to 1/100th. If it's below -1, we'll apply the same slope. And I've humbly named it Mick ReLU. So our function for this, well, let's make sure that we'll do our build configuration first, so we don't forget in the excitement of implementing it. So activation Mick ReLU, we'll pass that into the command prompt, and we've got to have a catch for it in our CMake file. So target compile definitions. We could just make it the default. All right, so if our input neuron is less than 1 and our input value is greater than -1, this is the standard case. So this is this section. Just the do nothing section. We return our value. We return what we got. So here we'll say else if our value is greater than 1, we'll apply a little formula to it. So we can think of this as, or we can just use our old, from, I don't know when you guys learned it, but probably a while ago, y equals mx plus b, like 6th grade or something. That is we can define a straight line with our function being the slope of the line plus the intercept, so the y-intercept. Because this is 1 over and 1 up, we know that it would, if it continued on, we didn't have this if statement in the way, it would intercept at 1 minus the slope. So if this was 2 away, it would be the intercept would be 2 minus 2 times the slope. So however far away it is in the x direction, you multiply that by the slope, you take 1 and you subtract that. And that defines this line for us. And the line in the negative case is similar. So let's do this. So mx, so activation slope. We don't have our activation slope defined. We will make it 1/100th, and then our inverse we will just we might use an inverse just to make sure the compiler is optimizing. We might use this inverse later on. We might not, we'll see. But it's there if we need it. So we've got activation slope defined. Return activation slope times n plus our intercept, which will be neural net float 1 minus our activation slope, and semicolon, because we're pros and we know to use semicolons every time. Now, instead of doing an else if to capture the last case and then do some type of defensive programming afterwards, instead of being defensive and safe, we're trying to go balls to the wall and be as fast as possible with our code, because we're going to be crunching these numbers millions and millions of times. So an else if has to do a conditional on it, and it'll jump if it's not satisfied. But we know that all cases are covered above. The other two cases are covered, so this third case, we know what it's going to be. So we're going for optimization instead of safety, and you'll see that a lot. In fact, so we'll go through, we'll write the code, we'll make it work, and I'll try to make it pretty readable. But then I'm going to go through it. I'm going to really chop things up and optimize it to get the most performance that we can out of it, or at least that I can provide. All right, so in this case, instead of adding 1 minus the activation slope, as you can see, if this were extended, we are going to just subtract 1 minus the activation slope. All right, activation make prelude. Now, so this would transform our data here. Come take a look, see what we see. Take a gander at our results. No, these values are the same. We want them squishified. That is the one we just opened. So activation make ReLU. Oh, we didn't save this file. This is a text editor, not an IDE, so it's not going to save our files for us. We're running through the command line, so that'd be a pretty fancy extension if it would auto-save before we compile. All right, now let's see. Nope, still the same data. Activation output. And we are printing our activation. I remember looking at that. These functions look weird without a return statement. Just name this activate, of course, or else it wouldn't compile. So if it's less than 1 and it's greater than -1, we turn in. If it's greater than 1, we do this. So this case would be it's less than -1. But really, they're all greater than 1. So our activation slope would be is 1 over 100. For our slope, let's use a power of 2. That way we can do some bit shifting magic for our float. 2 divided by 128. I can just change the exponent, which I think a multiplication takes 4 cycles. On Pascal generation, I'm on Turing, probably 4 cycles as well. With the bit shifting takes 1 cycle, then I think it has to do a bitwise and again. So that should only be 2 cycles. Maybe you can do it 1. So if our in value is greater than 1, here we have first layer output size. Let's make sure it's compiling this correctly. Pragma message activation make array loop. Here's where it compiles a file, so it should have been here after this. Oh, it's passing in deactivate nothing. Didn't I run? Yeah, I ran this script, 05. But you can see here. Let's look at the file it compiled. File writer, it's passing in -d activation nothing. Why is it doing that? Because oh, it's not deleting the directories. So it's the cache was messing it up. So that's some kind of bug in CMake where it caches a lot of information. Here we've got our CMake files. So we got this CMake check.cache. So if you don't just completely delete all the cache files, sometimes you get that bug. So every time I run CMake, I delete the entire build folder, make it, and all the cache files are in the build folder. So let's run it again. CMake build run. While it's doing this, I'm going to install PowerToys because my coworker told me about this, and this is an awesome tool. Oh. All right, back to the code. It said I did great. All right, that means it got here, so we know it's going to the correct spot. I think just on MSVC compiler, you have to, for Pragma message, you have to put parentheses and then your message in double quotes, unlike in GCC where you can just start typing in text. And I'm using Power Toys. I'm going to keep this window here to remind me where the audience can't see. So I just select this window and I do Windows Control T, and that keeps it on top. I'll shrink it a little bit. That makes a charming little chime. There we go. Now I can't see where you can't see. You guys can see most of it. Let's look at our activated data. All right, looks like we're on the right track. Except this should be like 1.07. I don't know, because we're subtracting 100th from it. So it's 1 minus 100, so 0.99 plus 100th of this. It should be a little bigger. Let's see how our end data looks. So 217 goes to 2.6875. Guessing it's, oh, we're using 128th now. Oh, that's right. Okay. So that makes sense. Sweet. All right, we do want to do, so with our architecture, first we add, well, first we convolute, we get our 32 arrays. Then we add them all together in one array. Then we batch normalize, and then we do our activation. And I wanted to skip batch normalization for now, except it's a really powerful feature. So let's just add it in. And in order to get our batch normalization, we need to be able to sum up a lot of variables. So that's an operation that's typically called reduce. And this will always be the same. It's always will be a reduction algorithm. So no need for any type of include guards. Or not include guards, but preprocessor branching. And this we'll do next episode because I'm getting hungry and sleepy. So to end this, we will commit today's work. So git add all, git commit message, added activations, and file writing of activated data. All right, I'll push it. So now it's available on GitHub for anyone that wants it. Just go in and clone that bad boy. And this, haven't tested on Linux yet. Probably have to configure your some CUDA directories on it. I will port it to Linux. Like I said yesterday, though, if you want to run this on Linux, I do have this in. This little thing might help. If anyone wants to run this on Linux, just ask, leave a comment, or message me, and I will prioritize compiling it for Linux. So I've got a Jetson Orin, so that's, and a Jetson Xavier, so that's ARM64. Linux Ubuntu 2004, I think, or 2204, and then on my computer I've got 2004 and 1604. So yeah, if anybody has any of those distros, I will I'll prioritize getting these compiled on those platforms. All right, just consistentizing our spacing here. All right, and any donations I get, I appreciate. That'll help me with this project. I've got a Patreon, also linked my Venmo account. So yeah, I'd greatly appreciate any donations for this project. All right, guys. Happy coding.